Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. I direct the actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to make a tax-deductible donation to support our students, please go to smarturl.it/help-ISU-actuary. Here's a problem for today. Let x and y be continuous random variables with joint density function equal to 8/3 xy when x is between 0 and 1 and y is between x and 2x and 0 otherwise. Calculate the covariance of x and y. So in a problem like this, which is more or less a standard expected problem on multivariate two-dimensional, so bivariate joint probability distribution. A very important step is to draw the graph showing you, a figure showing you where the joint density of x and y is positive. And in this case, that happens for x between 0 and 1. So you can see that on the x-axis, the point where you have x equal to 1 is indicated on this graph. And y is between x and 2x. And you have here the two lines where y equals x and y equals 2x indicated. And of course, for x equal to 1, the first line reaches y value of 1, and the second line reaches y value of 2. And then we are told that only for the values, for the set of values of x and y, such that y lies between those two lines, where y equals x and y equals 2x, the joint density is positive, and only for the range of x values between 0 and 1. And this is the way we establish the region that is marked with these dotted lines as the region where the joint density formula applies. Outside of that region, joint density is 0, and that outside is more or less irrelevant as a result. And remember that within the region marked in that figure that I just showed you, the joint density is 8/3 xy. Very important to remember that. Okay, so we calculate first the density of x, the marginal density of x. And that's the integral over all possible values of y for a given value of x. And of course, the values of x where you get positive density are only between 0 and 1. And for any specific x, y runs between x and 2x. So we take the integral over all possible values of y, which is between x and 2x, of the joint density, which is 8/3 xy, with respect to y, so dy. Okay, with respect to y, 8/3 x is a constant, so we only take the integral of y, which is 1/2 y squared, and we evaluate it from x to 2x. And once we do this, what we get is 8/3 x times 2x squared minus half x squared, which is 1.5 x squared, or 3/2 x squared. 3/2 multiplied by 8/3 gives us 4, and x times x squared gives us x cubed. So the density of x for x between 0 and 1 is 4x cubed. And therefore the expected value of x is the integral from 0 to 1 of x times the density, and that's the integral from 0 to 1 of 4x to the 4th, and that's 4/5 x to the 5th evaluated from 0 to 1, so it's 4/5. For the expected value of y, what we do is, well, we would evaluate the integral from 0 to 2, the possible range of values of y times f sub y of y dy. Of course, f sub y of y dy is the integral over all possible values of x that correspond to a specific value of y of the joint density dx. So I just write it in there, and then we change the order of integration. And now we actually have over the region where the joint density is positive, the integral of y times the joint density. That's actually an alternative way to calculate the expected value of y. You just take the integral of y times the joint density over all possible values of x and y. But we change the order of integration so that now we do the integral with respect to y first, and y runs from x to 2x, and then the integral with respect to x second. And you may wonder, well, can I do this? And the answer is, that's called the Fubini theorem, and it says that whenever the double integral exists, you can change the order of integration as long as you carefully evaluate where the calculation takes place. So you have to evaluate that region where the density is positive. Or alternatively, you can just remember that if the function whose integral you calculating is positive, then the integral exists, possibly infinite, but it doesn't make any difference. The Fubini theorem always applies for things that are non-negative. So we can just do the double integral the easier way, which is with respect to y first and then x, and for a given value of x, y runs from x to 2x. So this becomes the integral from 0 to 1 of the integral from x to 2x of 8/3 x y squared dy, and then integral with respect to x of dx. And with respect to y, 8/3 x is really a constant. The integral of y squared is 1/3 y cubed. So 1/3 times 8/3 is 8/9, so we get 8/9 x y cubed evaluated from y equal to x to y equal to 2x. And after we do this evaluation, we end up with integral from 0 to 1 of 56/9 x to the 4th dx. And of course the integral of x to the 4th is 1/5 x to the 5th, and 5 times 9 is 45, so this is 56/45 x to the 5th evaluated from x equal to 0 to x equal to 1, and that's 56/45. We could do what we did for x. We could evaluate the f sub y of y first, and then find e of y. So here is the evaluation of the density of y, and we have to split it into two subregions. Here is the reminder of what this looks like. If you have y between 0 and 1, then you are between the lines where y equals 2x and y equals x for the possible values of x. But if y is between 1 and 2, then the possible values of x are between those from the line y equals 2x and where x equals to 1. So here is this done exactly. If y is between 0 and 1, then we have two lines, y equals 2x and y equals x, but we need to translate them into what x equals in terms of y, which is x equals 1/2 y and x equals to y. And so that's the range of possible values of x. So we have first for y between 0 and 1, the integral from 1/2 y to y, 8/3 x y dx. And for y between 1 and 2, we have the integral from 1/2 y, that's x equals 1/2 y whenever y equals 2x. So that's along this line. But the upper bound for the values of x is 1, x equals 1. And we do, the calculation is of the same density, so it's 8/3 xy. Both integrals are with respect to x, so 8/3 y is actually a constant. And then we're taking the integral of y, which is 1/2 x squared. I'm sorry, integral of x, which is 1/2 x squared. And we evaluate in the first case from x equal to 1/2 y to x equal to y, and in the second case from x equal to 1/2 y to x equal to 1. So we get the formula for f sub y of y to be y cubed for y between 0 and 1, and 4/3 y times 1 minus y squared over 4 for y between 1 and 2. And then the expected value of y is the integral from 0 to 1 of y times y cubed dy, because that's the formula for the density of y between 0 and 1, plus integral from 1 to 2 of y times 4/3 y times 1 minus y squared over 4 dy, because we have a different formula for the density of y in the range of values of y between 1 and 2. So the first integral is the integral of y to the fourth from 0 to 1, which is 1/5, easily established. And the second one is the integral becomes 4/9 y cubed minus 1/15 y to the fifth, evaluated from 1 to 2. So we get the same answer for the expected value of y doing it this way, which is more complicated, but in many ways it's probably more direct. Anyway, the answer is that we get this evaluation of the second function integral from 1 to 2. We plug in the values, we get the same answer. We're looking for covariance though, so we're not done at all. We need to find the expected value of xy, because covariance is expected value of xy minus expected value of x times expected value of y. So the expected value of xy, what's a double integral of xy times the joint density? And of course the integral is much easier doing first with respect to y, with y running from x to 2x, and then with respect to x, with x running from 0 to 1, which is exactly what we're doing here. For the first calculation with respect to y, the expression 8/3 x squared is basically a constant, and we're really doing the integral of y times y, so y squared, which is 1/3 y cubed, evaluated from y equal to x to y equal to 2x. So we evaluate it. After we do this, we end up with, well, 8/3 minus 1/3, x cubed in both cases multiplied by these fractions, but 8/3 minus 1/3 is just 7/3, and then 7/3 times 8/3, that's 56/9. And otherwise we have there x squared times x cubed, so it's x to the fifth. So the integral from 0 to 1 of x to the fifth, well, that's just 1/6 x to the sixth. And of course, evaluate from 0 to 1, that just gives you 1/6. So the answer is 56/59 times 1/6, which is 56/54, the same as 28/27. And the value of covariance is established as this 28/27 minus 4/5 times 56/45, which is approximately 0.0415, which is answer A. Please remember this is copyrighted material. The problem itself belongs to the Society of Actuaries. The solution is mine. Good luck in your studies and good luck on the test.